Welcome to the session. Today I will be discussing about the shear force and bending moment diagrams for simply supported beams subjected to point loads, uniformly distributed loads. So in the last session we have discussed about the convention, sign convention for shear force. This figure shows the sign convention that we generally follow for shear force. When we consider a section, the shear force at that section is calculated as the algebraic sum of the forces acting either on the left side or on the right side of the section. Okay. So now the forces which are upwards on the left side and downwards on the right side are considered positive, and the forces which are downwards on the left side of the section and upwards on the right side of the section are considered negative shear force. So the bending moment also will be acting at all the sections. Okay. So the transverse forces acting on the beam causes shear force and bending moment. That means the beams are mainly subjected to shear force and bending moment, unlike columns which are subjected to axial forces. So the bending moment means it is the internal stress developed at any section resisting the external moment due to the applied loads. And the convention for sign convention for this bending moment is taken as shown in the figure here. Okay, the forces which cause upward bending or sagging are considered positive, and the forces which cause downward bending or hogging are considered negative. Okay, the effect of forces is to bend the beam. Transverse forces will tend to bend the beam either upwards or downwards. In the case of, for example, in the case of cantilever beam, the external loads bend the beam downwards, causing hogging bending moment, that is the negative bending moment throughout the beam. Whereas in simply supported beam, the external forces cause downward bending with concavity upwards, producing sagging moment or positive bending moment. Let us consider the problems on simply supported beams. Let us consider this problem. A simple problem on simply supported beam with a single point load acting eccentrically at a distance A from left support and B from right support. And the span of the beam is L here. So to start with, to draw the bending moment diagram for a simply supported beam, the very first step is to find the reactions at the supports. So the reactions at the supports are calculated by applying the static equilibrium conditions sigma m equal to 0. So now we can take the moments either about support point A or support point B, so that one of the unknown reaction is eliminated from the equations. So here we have considered the moments about A, and sum of moments about A is equated to 0 for equilibrium, algebraic sum of all the moments about A must be 0. So applying this condition, we have the moments due to reaction RB and the load W. The reaction RB produces anticlockwise moment and the force W produces clockwise moment. So we equate sum of anticlockwise moments to sum of clockwise moments. That is the meaning of this equation. Algebraic sum of all the moments is 0, or sum of clockwise moments is equal to sum of anticlockwise moments. So here we have the moment due to RB into L, that is anticlockwise, that is equal to W into A, force into distance, that is the moment. Okay. So RB is obtained from this as WA by L. WA by L. Now we can obtain RB by applying the condition sigma Fy equal to 0. We equate sum of upward forces and sum of downward forces. So here the upward forces are Ra and Rb, and downward forces only W we have. So the equation is Ra plus Rb equal to W, or Ra is equal to W minus Rb as shown here. So W minus Rb is WA by L. Okay. So W minus WA by L, that gives W into L minus A by L, and we know L minus A is equal to B, because A plus B is equal to L. A plus B is equal to L. So L minus A is replaced by B. Okay. So the reaction at B is, at A is WB by L. Once you find reactions, now we consider sections between, for every change of load, we need to consider one new section. Okay. So we have to consider sections between AC and BC. We need to consider two sections here. And the shear force at each section we will find out. Shear force and bending moment also. So considering the portion AC and considering section as X at a distance of small x from left support A. And this section is valid between the points A to C, and hence the limits for X will be from 0 to A. So the shear force at A at the section X is equal to, considering left hand side, sum of all the forces, algebraic sum of all the forces lying to the left of the section. So in this case, only reaction at A is to the left of the section. So shear force at section X is equal to Ra, and that is positive as per our convention. The convention for shear force is, if this is the section, left side upwards and right side downwards are positive shear forces, and left side downwards and right side upwards are negative shear forces. Okay, the forces to the left acting upward are considered positive, and to the right acting downward are considered negative. So in this case, we have positive shear force at X, which is Ra, that is WB by L. And if you observe here, it is independent of X, independent of the distance of the section. Here X defines the position of the section. Distance X defines the position of the section, okay, which moves from A to C. Understand? So here the shear force at all the sections between A and C remains the same, that is WB by L. Okay, that means it is independent of the position of the section in this case. So we can say in other words as if there is no load between any 2 points, then between those 2 points, the shear force remains constant. The shear force remains same between those 2 points. So we can conclude that when there is no load between any 2 points along the beam. Okay. Now, that means shear force at A and shear force at C are equal to WB by L. Okay. So we find shear force or bending moment at various sections along the beam, and we will plot the diagrams, shear force diagram and bending moment diagram, taking length along x-axis and shear force or bending moment along y-axis. Yeah. Considering now the bending moment at section X. This is again in the portion AC we are considering, okay, and X varies from 0 to A. So what is the bending moment at X? Considering left hand side again. So the bending moment at X is equal to algebraic sum of all the moments, means algebraic sum of the moments of all the forces lying or acting to the left of the section. In this particular case, we have only reaction RA to the left of the section. So the bending moment at X will be RA into X. And this is positive again as per our convention. Our convention is the forces acting upwards produce sagging bending moment, left side or right side, both sides. The forces acting upwards produce sagging bending moment. Okay, and this moment is taken positive. So here RA being acting upwards produces sagging moment, and hence it is positive. So RA into X. RA is WB by L into X. This is the bending moment. And if you observe here, it depends on X, means position of section. As I told you, X defines the position of section, and it varies from 0 to A. Okay. So bending moment here depends on X. That means it varies linearly with distance X. Okay. From point A to C. So now the bending moment at A, that means at X equal to 0, will get bending moment at A. By putting X equal to 0, we get bending moment at A, which is 0. Okay. Substituting 0 for X, we will get bending moment 0. Next, at X equal to A, we will get bending moment at C. Okay. Putting X equal to A. The bending moment at C will be WB by L into A. That is nothing but WAB by L. WAB by L. This is the bending moment at C. Okay. Next, coming to this bending moment at C, bending moment or shear force between the section in the portion BC actually. Considering portion BC, and here the section is considered with origin at B. In the previous section we have taken origin at A, but here we will take the origin at B. Okay. So we have the beam like this, simply supported beam, and load acting here somewhere, and this distance is B. So we consider the section here in portion BC and take the origin at B. So what is the shear force at X? It is nothing but RB. Only force considering right hand side is RB, and it is upwards. So as per our convention, right side upwards is negative. That's why we have taken here minus RB. And what is RB? We have calculated the reaction minus WA by L actually. RB is WA by L. So shear force is minus WA by L. Okay, and it is independent of X. Shear force is independent of X. So as we have discussed in the previous case of section AC, there is no load between B and C. Therefore, the shear force remains constant between B and C. Okay, understand? So the shear force, actually this is B and C, not A. Shear force at B and shear force at C are same and equal to minus WA by L, as it is independent of position of section. Okay. Yeah. Coming to next, bending moment. Bending moment at X, considering right hand side. So what are all the forces acting on the right hand side? Only reaction RB here is acting towards right. So the moment due to RB is RB into X. This is again positive. Shear force is negative because right side RB is acting upwards. But coming to bending moment, the upward force produces a sagging bending moment, and hence it is positive. Okay, RB is WA by L into X, and this is dependent on X, position of section. Okay, yeah. Substituting X0, you will get bending moment at B. Substituting X0, you will get bending moment at B, which is 0. And substituting X equal to B, you will get bending moment at C, WA by L into B. WA by L into X is B. So WAB by L. WAB by L. Understand? So, knowing these values, we can plot the bending moment and shear force diagrams. So, we have calculated at various points the bending moment and shear force. Now, we will plot the shear force diagram and bending moment diagram. Yeah, this is the shear force diagram. Actually, the convention that is followed in this problem is opposite to that what we have followed. Actually, the shear force diagram will be, according to our sign convention, is positive between AC and negative between BC. Okay, so this is positive shear force, which is WB by L, and here WB by L, and WA by L, negative. Okay. Now, if you observe, the shear force at C changes from plus WB by L to minus WA by L. Okay. That means the sum of these values WB by L and WA by L is equal to W into A plus B by L. A plus B is nothing but L, so it is equal to W. Okay, that means at C we have a point load. Okay, so at the point of application of point load, there will be a sudden drop in the value of shear force. Sudden drop or sudden rise in the value of shear force by an amount equal to the load acting at that point. Okay, yeah, here the shear force varies from plus WB by L to minus WA by L. How will you get this? By subtracting W here. Okay, it drops from WB by L to WA by L, minus WA by L. Okay, yeah, WA by L is nothing but WB by L minus W minus W. It is clear? Yeah. This is incorrect. Incorrect in the sense it is correct because the convention followed here is opposite to that what we have defined. Okay, you can follow this convention also, it doesn't matter. Okay, anything is okay, but the general convention that is followed is this: left up or right down or positive for shear force. Okay, yeah. Coming to bending moment diagram, the convention here is same: sagging positive and hogging negative. If it has been taken the same as we have assumed. Okay, so bending moment at simple support will be 0. That is that you can uh, take granted because the simple support does not restrain any rotation, so no moment is produced, and hence this moment will be 0 at simple support. Okay, at fixed end you will have moment developed, but at simple support, that means at roller support or hinge support, the moment is 0. That is in case of end supports we are talking about. Okay, and bending moment at C is WAB by L. So you plot these three values, and being a linear variation, these points are sufficient for us to draw. Okay, understand? End points will be sufficient to draw the diagram. Yeah, this is WAB by L. Is this clear? Yeah. So this is the simple case in simply supported beam. Okay, with a single point load. So what are the points to be noted here? The bending moment at supports will be 0. In case of simply supported beam, the bending moment at supports is 0. As they do not restrain rotation, they do not produce moment. So bending moment will be 0 at simple supports. Okay, that is one point to be noted. And what else? The shear force remains constant. If you observe between A and B, shear force is same because there is no load between A and B. If you observe the loading diagram, there is a load at C, and between A and B there is no load. Similarly, between B and C there is no load. So, between A and C, the shear force remains constant, WB by L. Similarly, between C and B, the shear force remains constant, that is WA by L. Understand? So, these points are to be noted. Okay, it will be helpful in drawing shear force diagrams and bending moment diagrams. And in case if there is no load between any 2 points, the bending moment diagram will be an inclined line. That means it varies linearly with along the span actually, along the span. The bending moment varies linearly between those 2 points where there is no load acting. Okay, that means between A and C, the shear bending moment varies linearly. Similarly, between B and C also, it varies linearly. Okay, that means it is a straight line. Okay, it depends on x. Y is equal to some constant into x. That is the equation for bending moment. Okay, is this clear? These are the points to be remembered. Next, let us discuss the other type of load, which is distributed load. And in distributed load, you have 2 types. One is uniformly distributed, and second one is uniformly varying. Ante uniformly distributed load means rectangular load actually. That means the intensity of loading remains constant. Such a load is said to be uniformly distributed. Okay, and uniformly varying load. Uniform variation means straight line variation. That means it is a triangular load, something like this. It is rectangular load. UDL is rectangle. Okay? This load which is shown here can also be shown as a rectangle like this. Okay? Yeah. UDL can also be represented like this as a rectangle. Understand? Both are correct. So here the intensity of loading is given as W per unit length. Intensity of loading is given as W per unit length. Here the length of beam is L. So for unit length it is W. So for total length L, the total load is obtained by multiplying the intensity with the length of UDL. Okay. So total load in case of UDL is given as intensity multiplied by the length of loading, not the length of beam. It is the length of loading. For example, on a beam, if load is acting only for a length L, length A, then the total load is W into total load is W into A, W into A. A means the length of UDL, where the length of beam is L. The length of beam is L. Okay. So the total load of UDL is calculated as the product of intensity of loading multiplied by length of the load, UDL. Understand? And the resultant of this load, okay, total load, acts at midpoint of UDL. Okay, from the end of UDL, it will be at its middle. Okay, A by 2. From end of UDL, the resultant load W, which is equal to W into A, acts at the middle, means at a distance of half of the length A. Okay. Similarly, in this case, the resultant load WL acts at a distance of half of the length L, that is L by 2. So here half of the length means it is the length of UDL and not the length of beam. You keep that in mind. Understand? So in this case, the loading is symmetrical. Okay? Understand? So when the loading is symmetrical, then the reactions will be equal. The reaction in case of simply supported beam we are talking about. If the loading is symmetrical, you know what is symmetrical loading? Okay? Yeah. From the center, it is distributed the same manner on either side. Okay? Such a loading is said to be symmetrical loading. If you have point load here on one side at a distance of say small a, this is not symmetrical. If you have one more load here on the right side also at the same distance a from the right end, then this load becomes symmetrical. Okay? This load becomes symmetrical. So like once you find that the load is symmetrical, then the reactions, support reactions will be equal. Okay? And equal to what? Equal to half of the total load. Half of the total load. If there is only UDL acting, then if there is only UDL acting without this point loads, then RA and RB is equal to WL by 2. Okay? If you have 2 point loads here, symmetrically placed on either side, then say W placed at a distance of A from either side, then the reaction is W plus WL by 2. Okay. So total load is 2W, total load 2W plus WL. So half of this is by 2. So W plus WL by 2. That is the reaction at one support. Is this clear? Let us now discuss only about uniformly distributed load. That is rectangular type of loading. Okay. So in this case, the loading is over entire span. The loading is over entire span. Okay. The loading is acting on entire span. So the reactions are W each, not W, WL by 2 each. Okay. So now we have to consider the section. We have to consider section, and we have considered the section at a distance x from left support. Okay, at a distance x from left support, and if you observe, there is no load acting other than UDL. Okay, but there is no change in loading. Same loading is acting from one end to the other end. If we have any point load here at some point on this span, then this load breaks. Okay, the shear force or bending moment equation that is calculated at x is valid from one end to the other end if there is no point load here. Okay, that means the same section is valid between A and B. For example, the shear force at section X is, considering left hand side, you have RA, that is WL by 2 minus this is upward, and what is the downward force? The total load on the left side of the section. Total load on the left side of the section. So the length of UDL on the left side is X, and intensity is W per meter, isn't it? So what is the total load for a length of X? W into X, isn't it? So this X now can be varied from 0 to L. The same section is valid from one end to the other end. Same equation is valid for shear force from one end to the other end. Okay. Similarly, for bending moment also. Bending moment at X is RA into X, WL by 2 into X minus, what is the bending moment? Bending moment at any section is sum of the bending moments of all the forces. Sum of the moments of all the forces acting on the left side or right side. Here we are considering left side. So RA into X, RA is WL by 2 into X. This is sagging bending moment, positive, minus the UDL, which is acting downwards, produces downward bending, hogging bending. So that is negative. So what is the total load due to UDL? It is WX, isn't it? WX. And at what distance it acts? Resultant. The resultant of this acts at the centroid of this portion. So this is WX, which acts at the middle of this portion. That means at a distance of x by 2. So the moment of the force WX is WX into x by 2. It is clear. So WL by 2x minus WX square by 2. This is the bending moment equation, which is also valid from one end to the other end. One end to the other end. It is clear. So now, by giving different values to x from 0 to L, we will get shear force at different sections and also bending moment at different sections. Okay. Yeah, by finding out shear force and bending moment at various sections, we will plot the diagram. Okay. Yeah. Now let us see the reactions are calculated, as I told you, by using the equilibrium condition sigma ma equal to 0. That is for general case. But for the case of being in which the loading is symmetrical, we can directly take the reactions as half of the given loading. Okay. In this case, the loading is symmetrical, so the reactions we can directly take without applying this equation. We can conclude. Okay. Yeah. By using this also we can find out. Okay. So taking moments about A, we have moment due to RB as RB into L, and that is anti-clockwise, and moment due to load UDL, that is WL is the total load, and which acts at the middle at a L by 2 distance. Okay, so WL into L by 2. So from this you will get RB equal to WL by 2, and hence RA is also equal to WL by 2. Understand? So after finding reactions, we consider the section now between AB. Only one section is sufficient here, and the limits for X will be from 0 to L. Okay. So the shear force at X is RA minus WX. Okay. RA is equal to WL by 2 minus WX. Okay. Understand? So here if you observe, for UDL, the shear force depends on position of section. And as the section moves, the shear force changes linearly. Okay? With the distance. From this equation, it is clear. The shear force at any section is given as WL by 2 minus W into X. Here X defines the position of section. Okay? Which varies from linear 0 to L. It is clear. Yes. So shear force at X equal to 0 is that is at X equal to 0 means section will be at A. So shear force at A is WL by 2 minus W into 0. Okay, that is 0. So it is WL by 2. Shear force at A is WL by 2. And shear force at bending moment now. Bending moment, you can find shear force at B also. Shear force at X equal to L is equal to WL by 2 minus WL. That means minus WL by 2. Okay? That means shear force at B at X equal to L means at B. Shear force at B is minus WL by 2. So if you observe that shear force at A is plus WL by 2 and shear force at B is minus WL by 2. That means the shear force is varying linearly from positive to negative. Positive to negative. Plus WL by 2 at A to minus WL by 2 at B. When it is changing sign, at some point it becomes 0. And when it is varying from positive to negative from one point to the other point, in between there lies a point where the shear force is 0. Understand? And at that point the bending moment will be maximum. Okay? And that we will see later. The relation between shear force and bending moment, that we will see later. So this is about shear force. Now coming to bending moment. Bending moment at X is considering left hand side of the section. Okay? Yeah. You have the load like this. Yeah, WL by 2 here and X. So what is the bending moment at this section X? WL by 2, that is RA into X. Okay? WL by 2 into X minus WX into At what distance it acts? At a distance of x by 2. So Wx into x by 2. So this is the bending moment. Okay. So this varies parabolically. If you observe here, it depends on x square. Bending moment depends on square of the distance. That means the curve will be a parabola. The bending moment curve will be a parabola. Okay. And bending moment at x equal to 0, that is at A, is equal to bending moment at A is equal to, so it is 0 actually. Substituting 0 for x. Okay. Substituting 0 for x. Similarly, bending moment at B, that is at x equal to L. So what happens to WL by 2 into L minus WL square by 2. This is also 0. WL square by 2 minus WL square by 2. So bending moment at B is also 0. Already we have told the bending moment at simple supports will be 0. Understand? The bending moment at simple supports is 0. And bending moment at C, the center, at x equal to L by 2 at the middle. Okay? Yeah. If you find the bending moment at the middle, WL by 2 into L by 2 minus W by 2 into L square by 4. So WL square by 4 minus WL square by 8. WL square by 4 minus WL square by 8. So it comes out WL square by 8. This is the bending moment at mid span, which is maximum. It is maximum because the shear force at x equal to L by 2 is 0, changing sign. Okay, that you can get from by equating this shear force to 0, you will get x equal to L by 2. At x equal to L by 2, the shear force is 0, and hence the bending moment at x equal to L by 2 will be maximum. So coming to the bending moment diagram we have to draw, isn't it? This uniformly varying load, we will be discussing this later. Yes, coming to the bending moment diagram for the given beam with the uniformly distributed load. With uniformly distributed load, W per meter. And the span is, and we consider section with origin at A. Okay. Now the shear force diagram for this will be plus WL by 2 here and varies linearly to minus WL by 2. Okay. And the variation is linear, so that it will be linear. At some point, the shear force changes sign. Changing sign means becomes 0. Okay, and the distance is obtained as L by 2. Okay, by equating the shear force equation, which is WL by 2 minus WX to 0, you will get x equal to L by 2. That means at x equal to L by 2, shear force is 0. Okay, and coming to bending moment diagram. At A and B, the bending moment is 0, and at C, the bending moment is WL square by 8, and the variation is parabola. What is the bending moment equation? WL by 2x minus WX square by 2. Okay, so this is the equation for bending moment, and the middle portion at the center, the bending moment is maximum and equal to WL square by 8. So we can also say that at the point where the shear force changes sign, the bending moment is maximum. Okay? Yeah, we obtain this relation later. For now, you do remember this. Is this clear? With this, I end this session. Yeah. Let us discuss some more problems in the next session.
Like, share and subscribe. Hit the bell icon for more updates.